All right, good afternoon, ladies and gentlemen, and welcome to XMod Systems' final product presentation for the Portable Test Stand Mark-I. I'm David Senecal, the design team lead, and with me today is Trey Buchanan, Joanna Faulkner, Frank Cephaletta, Nicholas Nagy, Rogelio Quintana, and Stephen Woodard. First off, I'll be going through the project overview. So the purpose of this project was that initially Embry-Riddle Aeronautical University lacked appropriate testing facilities for RC power plants and drone power plants. And this was acutely felt by such people as future prelim engineering groups and detail groups, the campus American Institute of Aeronautics and Astronautics Design-Build-Fly teams, and the up-and-coming Unmanned Aerial Systems majors and clubs who could use such a testing device. The scope of our project was to design, build, and test a portable modular test stand that would work for radio control and drone propeller power plant combinations, and quantitatively measure performance parameters such as thrust, downstream wake velocity, and revolutions per minute. Some of the specific requirements that we had to fulfill for the physical attributes of the test stand were modularity, and that had to accommodate a wide variety of propellers that could come in a variety of sizes between 10 inches to 27 inches in diameter, could be in push or pull configuration, and could be powered by internal combustion power plants or electric power plants. So some of the qualities of the test stand were that it had to be self-powered, and that, with the exception of the laptop, that the test stand could be on its own. And this was because the test stand also had to be portable, and that it could be moved to anywhere on campus and tested there. And when it would be moved, it had to be moved by 2 people. And this was so that our weight requirement would be 60 pounds or less and would be easily carried by 2 people, excuse me. And then on top of that, we had some safety requirements such as an anchoring system that would be self-contained to make sure the test stand didn't move during testing, and safety shielding to protect the users during testing. All this had to be done for a budget of $1,000 or less. Some of the data acquisition and analysis requirements that the test stand had to fulfill were some simultaneous data output requirements for the downstream wake velocity, axial thrust of between 2 to 50 pounds of force, propeller RPM, and fuel flow rate for internal combustion power plants, and power draw for electric power plants. All this had to be done with an accuracy of 5% full-scale output with an objective of 2%. And this had to be done with a data acquisition rate of 10 times the propeller RPM. The deliverables that we've delivered is the portable test stand Mark-I, the PTS Mark-I that you see here on the counter to my left. We've also created an operations and safety manual and created some data acquisition analysis code for future users. I'll now be handing off to Trey Buchanan.
Thank you, David. I'm now going to go over the design of the portable test stand Mark-I as is fabricated. To start off, we're going to give you a brief overview of the CAD rendering that was created in our preliminary design phase, compared side by side to the final fabricated product. As you can see, we decided to utilize a vast array of colors for the test stand for 3 main reasons. 1, aluminum is very difficult to look at in direct sunlight. 2, the colors allow easy callouts in the operations and safety manual. And 3, it looks much nicer than it did with just the aluminum. So the portable test stand can be divided into 6 main components. The first being the base frame, the second being the crossbeam, 3 is the mounting bracket, 4 the test surface, 5 the safety shielding surrounding it, and finally 6 the pegboard rail extension. We're going to go over each of those components in a little more detail. So for the base frame, we constructed or designed this with 3 main design points. 1, that it would have a self-contained anchoring system integrated with it. It would satisfy our portability constraint by utilizing a storage bay and handles, and giving us a modularity accommodation for both push and pull propeller configurations. For the anchoring system, we chose to utilize a rubber base made of neoprene 70 short A at 1/16 inch thickness. This neoprene that we chose to gives us a high coefficient of static friction for the asphalt and concrete surfaces that we would be subject to testing on from 0.6 to 0.9. Grass is also another testing surface which falls slightly lower than those coefficients of static friction. That rubber base is complemented by an auxiliary weight system consisting of a single 25-pound weight plate that has a location dependent on the testing orientation that we will again elaborate on where that location is a little bit further. For the portability method of the base frame, there are two main components to that. One, it has a storage bay located between the test surface here and the base frame itself. And this storage bay is large enough to house the crossbeam, the mount brackets, shielding, and all the instrumentation during transportation to and from different locations. Additionally, it has handles located on the front and the rear, which allows users to lift the portable test stand up from the ground and then can be proceeded to be holding it and carried with two hands. For our modularity accommodation, we have installed two sets of fitted columns that allow the crossbeam up here to be mounted in either the center fitted columns, as is shown on the test stand currently, for our pull configurations, where the propeller would pull it forward, and in the push configuration, which means the crossbeam would be flipped, mounted in the front mounted fitted columns, and then would be pushed forward. For the crossbeam itself, this was the main component that allows us to integrate the propeller power plant combination onto the test stand itself. The crossbeam was constructed out of a single 6-foot piece of aluminum box beam that was then cut with 4 45-degree welds and welded together to create a solid piece. This solid piece structure gives us the highest rigidity that would be available as opposed to creating it out of multiple segments with a wall thickness margin of safety of 13.2, and this is with a testing thrust range of 75. So that's already giving us a factor of safety for the testing, and this ensured that our crossbeam would not be a point of failure during testing. Additionally, it has foam padding at the bottoms for a secure fitment that also help to dampen our horizontal vibrations. And not pictured in here is foam padding located at the base of the fitted columns. It also aids in vertical vibrations that may occur. A little close-up of the mount bracket and its crossbeam integration itself. As you can see in the left-hand side of the picture is the X-pattern front plate. That's where the power plant would actually be affixed to the crossbeam. And then on the right side is a load cell back plate, which houses the load cell. The way this structure works is with the engine outputting thrust, it actually pulls the entire front plate forward. And what that does is with the load cell located back here, it allows the load cell to be pushed up against the crossbeam, which gives our thrust output. For the mounting bracket, a little more specifically, this X-pattern front plate can accommodate all vertically mounted power plants that would be within our testable thrust range of 2 to 50 pounds. The largest power plant that we could be subject to testing is the DLE-85 with its orientation of the mounting pattern shown overlaid on the mounting bracket, and the smallest with the E-Flight Power 10, again showed overlaid the mounting bracket. The small circle in the center of the mounting bracket is used to accommodate both the chuck for electric power plants to protrude through the mounting bracket, as well as provide an air inlet for the carburetors for the IC engines. The test surface serves two purposes. The first is that it provides a boundary between the testing wake field and the instrumentation hardware that is located on the base frame underneath, and it also denotes a no stand zone denoted in the red on the picture. What this no stand zone is essentially if you take those red outlines and extend those about 10 feet outwards, that is the area that we have in our user manual and operations and safety manual for any testing users to not be within that range. So essentially they remain on either side of the test stand. For the safety shielding, its main requirement was that it had to surround the entire testing section. This meant both radially outwards in all directions and providing enough depth to satisfy both our push and pull configurations. The picture on the left-hand side of the slide denotes for our largest power plant, we have between 7 and 8 inches of clearance between the propeller and the edge of the shielding, and it also surrounds the entirety of the box. The dimensions are 36 by 40 inches tall, 36 inches wide. This dimension was governed essentially by our largest propeller that we could be subject to testing of 27 inches. We wanted to make sure that we provided enough area around the propeller to allow tip effects to occur and not obstruct the data that could be acquired downstream. So we've given it about a 10% margin between the tip of the propeller and the safety shielding. The final material selected was a Macrolon sheet at 0.18 inch thickness, which We will go on to the testing a little bit later as to why that was chosen. Finally, for the pegboard rail extension, this was meant to allow us to mount our downstream wake instruments, such as the thermocouple and pressure probes, up to 2 times the maximum propeller diameter away. During the preliminary design phase, we found that in order to accurately convey the wake field characteristics, you need to be at least that 2 times propeller distance away in order to quantify your velocity data. And so this pegboard rail extension gives us a length without a weight penalty of having an increased area of the base itself. Finally, a little summary of the cost and weight of the portable test stand Mark-I. The cost actual shown of $175 is a build as is. If you were to go out and construct this on your own budget, that's what it would cost. The shielding is highlighted because it was donated by the College of Engineering, thankfully, and was therefore not included in the overall cost of the system. Lastly, the weight ended up being 9.3% over our RFP requirements, and this was due to a incorrect shielding that was actually given to us. We had ordered an 8-inch thickness and received a 0.18 inch thickness. So that added weight put us over the expected weight that we would have for the portable test stand Mark-I. I'll now hand it off to Joanna Faulkner.
Thank you, Trey. I'm going to go over some of the main structural testing that we did for the test stand in order to ensure that it would be able to stand up to the needs. For our test stand, we had to look into 2 different kinds of structural testing, being shielding and anchoring. Within shielding, we needed to ensure that in the event of failure, it would be able to withstand a certain impact. And with anchoring, we needed to ensure that it would not slip or tip during testing. For shielding, during our prelim phase, we did some calculations using 2 worst-case scenarios in the event of propeller fracture during testing. In the first case, we said it was going at the maximum RPM, in which case it would be the fastest thing hitting our shielding. And in the second case, we said maximum propeller diameter, in which case it would be the largest thing hitting our shielding. From these calculations, we found that the maximum kinetic energy that our test stand would have to be able to withstand was 435 foot-pounds of kinetic energy. For our testing considerations, we took those 435 foot-pounds and said the worst-case scenario was if it hit as a point force on the surface of our shielding. For this reason, we started looking into polycarbonate plastic at 0.118 inches of thickness, and testing that was conducted on this yielded no failure, meaning that there were no cracks or no dents that were greater than half the thickness of the shielding material. As Trey mentioned earlier, the actual material that we received after ordering was 0.18 inches thick, which was nearly twice as thick as the material we tested with, giving us an extra factor of safety that our material would not fail under impact. In order to test our shielding, we used a pressure launcher with potatoes that had propellers impaled into them, and the potato was then wrapped before shooting so that it wouldn't break apart any sooner in the process than it needed to. From our testing, again, we compared our results of our testing to the initial calculation of 435 required foot-pounds of kinetic energy without failure. And again, with the 0.118 inch thick sheet, we found that at the highest pressure to achieve the velocity from the potato launcher, we got a kinetic energy of 471.2 foot-pounds of kinetic energy. From this impact, we found that the propeller was more inclined to deflect off of the shielding before cracking or causing significant dents, although there was some visible surface scarring. In order to test for anchoring, we were looking for 2 main considerations: whether the test stand would slip or whether it would tip. For slip, we used the anchoring consideration of rubber, in which case it would keep the test stand from sliding forward on the ground under the force of the thrust. For tip, we utilized auxiliary weights to ensure that under the highest thrust that we would be meeting, the test stand would not rotate forward about the x-axis during testing. For our anchoring considerations, we considered first of all the surfaces that the test stand would be used on. Our main surfaces that we expect the test stand to be used on would be concrete and asphalt, and so we tested the test stand on these surfaces outside of the prop lab and on the asphalt surface behind the prop lab as well. Also, for our testing considerations, we had to consider the test stand in both push and pull propeller orientation, where push propeller orientation They are mounted in these front fixed beams, and in pull propeller, they are mounted where it is seen right now. For our testing, we put the thrust at the center of the mount bracket, meaning we pulled at this point here to see if failure would occur. In order to test, we fully assembled the test stand as it is seen to your right, and force was applied to the bracket as I showed you using a fishhook scale so that we could measure the force as it was happening. Force was applied up to and past slip or tip occurrence to see if we could get both failure modes to occur. For the testing, we used both weighted and unweighted considerations, in which case weighted was taken with the extra 25 auxiliary pounds of weight that we had to add to our test stand, giving us a total weight of 90.6 pounds, and unweighted was given with the 65.6 pounds of the test stand's weight by itself. Our results for tip showed that in pull configuration, there was no point at which the test stand tipped. It was more inclined to slip, and after slipping occurred, even under additional force up to a reasonable point, tip did not occur. However, in the push configuration, unweighted, the test stand was inclined to tip at about 33.5 to 35.5 pounds of thrust. For this reason, we would advise that if users expect their thrust to exceed 30 pounds, they do use the auxiliary 25-pound weight that we have on any point in the test stand. For slip, we found that in both pull and push configuration, on the particular surface we tested at, the test stand was unable to meet the 50-pound requirement max, again, reaching about somewhere between 30 to 42 pounds of thrust before it started slipping. For this reason, again, we would advise users that if they expect their test stand to be going over 30 pounds of, or if they expect their power plant, rather, to be going over 30 pounds of thrust, that they use the auxiliary weights, again, at almost any point on the base of the test stand. Next, I'm going to hand off to Frank Cephaletta and Nicholas Nagy.
Thank you, Joanna. We'll now be going over the instrumentation hardware of the PTS Mark-I. An overview of the instrumentation hardware includes the current state of our instrumentation we are implementing, the instruments that are tested and integrated, tested and not integrated, and both not tested and not integrated, as well as a schematic of all the instrumentation. In terms of the instrumentation we actually utilized, all 10 of the required instruments we did acquire, 8 of which we managed to test to the keel probe and static probe. We did not test due to time constraints, and fully integrated 5 of the 10 instruments due to the fact that we'll not be testing internal combustion engine power plants on the PTS Mark-I. As for the tested and integrated instrumentation, we'll be going over the DAC, the breadboard, load cell, the optical sensor, and finally the watt meter. The data acquisition device we decided to use the DAC is the USB DAC model 6001 with a sampling rate of 20,000 samples per second, or about 3,300 samples per channel with 8 total channels, which meets a requirement of 10 times the sampling rate of the highest RPM we could expect. All of the instrumentation that would be connected directly to the DAC would be the load cell, the pressure transducers, and finally the thermocouple. The breadboard, as another part of instrumentation, serves as the hub of, or basically the terminal where all of the instrumentation goes through the DAC and others, an additional amplification and filtration characteristics. Our breadboard currently uses an op-amp LM324 to amplify the load cell voltage. And for the future, we plan to replace the breadboard with a printed circuit board that fully integrates all of the instrumentation that we need, as well as keeping any of the wires from getting loose. And I will now pass it off to Nicholas Nagy.
Thank you, Frank. For the load cell, we decided to choose a FUTEC. This is a push-button load cell. and it is designed and capable of for both the push and pull configuration. This load cell has a range from 0 to 100 pounds of force, which of course reaches and fulfills the requirement of up to 50 pounds of force. This specific load cell was donated by the Propulsion Lab. The reason is the original load cell that we purchased, which was the Smack-In load cell. It would not fit on the load cell backplate, and not only that, we could not find any data online. This is simply due to the fact that we purchased this load cell off of Amazon. For the load cell testing, we conducted 2 days of tests, excuse me. The first day was with the E-Flight Power 60 with an 18-inch propeller, only in the pull configuration, but with this, we were able to test at both a clockwise and counterclockwise rotation. For day 2, we tested with an equivalent of an E-Flight Power 10, which was the smallest power plant that is to be seen on the PTS Mark-I. This was tested with a 10-inch propeller in a pull configuration. From both of these tests, we were able to gather data to see and compare, gather data to the calculations that we have made. Next is the optical sensor. We chose the Uni-T. This is a handheld tachometer, which was donated by Mjolnir Propulsion. It is USB capable, which means that it can connect from the actual tachometer to a computer for real-time data updates. It has a range between 10 RPMs up to almost 100,000 RPMs. We only expect to see up to 12,000 RPMs, so this again fulfills the requirement needed. The only issue that we see with this is that it is hard to see in low light conditions. It is hard to test in in high light situations, I'm sorry. For the other optical sensor that we were originally having, it has a lower sampling rate and a faulty product. We emailed the company, and yet the company has still not emailed us back. For testing the optical sensor or the tachometer that we have, it provided a real-time updates with the additional software. And again, we were able to export the data that was found onto an Excel spreadsheet for time and RPM. The complications that we ran into was that it required 2 laptops. This was due to the fact that we cannot run both LabVIEW and the additional software on the laptop that was provided. And again, it was unable to test in direct sunlight. This is due to the laser on the tachometer could not read the propeller or the the power plant. Next is the watt meter. It is capable of handling up to 5,000 watts. This is more than we should be able to see. It measures amperage draw and as well as utilizing universal connections. With the universal connections, the connections that we have on there are the universal connections. However, if the connections that we have do not fit the connections that the power plant provides, there are other add-ons and additionals, that can be purchased. For testing, we measured the accurate amperage draw during the second testing day. This again was because during the first testing day, the connections that we had were did not coincide with the connections that were available for the power plant that was provided. Next section is the tested but not integrated. These two instruments were initially tested. However, further testing is needed in order to be able to sufficiently integrate them within the PTS Mark-I. For the pressure transducer, we initially applied an air current into it and we were getting a signal. However, that signal was very noisy and very small, so in order to further test it, we would recommend an amplifier as well as a filter. And we recommend for further testing to provide a controlled current, be a blower or a compressed air. The kitchen scale that we use, this is for fuel flow. was initially tested by applying a load to it. However, we weren't sure if that load was accurate, so for further testing, we recommend providing known values and weights and seeing if those weights coincide with what is reading on the kitchen scale. The not tested and not integrated, these three instruments, have not yet been tested. Again, this is due to time constraints. And in order for us to be able to test them, for instance, the keel probe and the static probe, a air current needs to be provided into the probes in order to check for for air current throughout the tube. For the keel probe, it needs to test for angularity in order to be tested, or in order to be integrated within the test stand. And for the static probe, it needs to be tested for accuracy using a pressure transducer. For the thermocouple, recommended testing would be subjected to a known value, i.e. an ice bath, knowing the value of the ice bath, or the temperature of the ice bath. And for actual integration into the test stand, we recommend using an air current over the thermocouple to test to see if it is reading accurately. The next section I'd like to get into is the instrumentation placement on the PTS Mark-I. But before I go into that, I'd like to note that I have separated this section into 3 parts, A, B, and C. A being the test stand base, B being the crossbeam, and C being the load cell backplate. For the test stand base, the figures in blue denote the instruments with their correlating numbers shown on the left. The brown shown above is the pegboard, and the rest of it is the test stand. The thinly dotted lines denote wires directing from the instruments to the breadboard, as well as thick arrows. Those arrows denote tubes leading from the pressure transducer to the keel probe and static probe. The Q1 and Q2 denoted are quick disconnects. Those are to allow the user to easily connect and disconnect their instruments that are located directly on the crossbeam, as well as the load cell backplate, to allow them to be able to move the crossbeam from either a push or pull configuration or to store it for portability. The next is the crossbeam. This is our front view of the crossbeam. Again, the instruments with their numbers are correlated onto the left, and it utilizes quick disconnects at the bottom, quick disconnects 1 and 2. Quick disconnect 1 is located at the top. This is because the load cell is located directly onto the load cell backplate. And with the load cell backplate, this is the expanded view of it. There is, of course, only one instrument on the load cell backplate, and that is the load cell, with its corresponding quick disconnect. Next, I'd like to hand it off to Rogelio Quintana.
Thank you, Nick. I'll be going over the instrumentation software for the PTS Mark-I. I'll be going over the LabVIEW front panel, the direct measurements that the LabVIEW takes from the sensors, the tachometer interface software, the parameter calculations in LabVIEW, and the outputs that LabVIEW gives. Our current iteration of the front panel includes a measure button that you click once to begin collection of the data, click again to stop collection of the data, and because through limitations of the hardware and formatting of the Excel, the program crashes at approximately 20 seconds. Because of that, we have an indicator for the time elapsed for the testing, for the user to know how long, for the user to not reach that 20 seconds per test. On the bottom, there's a voltage indicator and a thrust indicator. Those are to show the current thrust and voltage, and also to show that if no load is applied but those numbers are not zero, the user can know that there is a zero offset error and to adjust the back plate to get that zero. To the right, there's the stop button to stop the testing if testing is over or there's any error. In the future, once all instruments are fully tested and integrated, user will have the capability to input keystroke inputs onto the front panel, which include the initial and final mass of the internal combustion fuel tank engine and the propeller diameter for any given prop that is being tested, and the atmospheric temperature for the thermocouple to be used as the cold junction reference. Currently, the LabVIEW can test thrust with the load cell. The picture above is the code used for the thrust. Simply it takes the data from the load cell, converts the voltage values to thrust, and outputs the data every 10 milliseconds onto an Excel sheet. In the future, as previously stated, once all instruments are fully tested and integrated, the test stand will be able to measure static pressure and total pressure from both pressure transducers and temperature from the thermocouple. The LabVIEW can output Excel data sheet that matches 8 times our max RPM, which equates to 10,000 samples per second. Due to limitations of our laptop hardware, we're not currently able to reach the 10 times our max RPM. Also due to the limitations of the laptop hardware, our front panel cannot currently output real-time graphical data, but with the Excel spreadsheet, the user can create their own plots. The picture to your left is a real data of one of our tests. The picture to our right is one of several iterations of a front panel that we would wish to incorporate in future iterations of our LabVIEW testing. The UT372 tachometer interface program, it displays RPM both numerically and graphically in real time, and allows the user to export the data also onto an Excel sheet. From there, the user can create their own plots for RPM. The image to your right is a real test of RPM full power. As previously stated, once all instruments are fully integrated and tested, there will be code within the LabVIEW to calculate 4 parameters, one of which includes the air density, which inputs the static pressure from the static probe and the temperature from the thermocouple. The second parameter will be downstream wake velocity, which takes the total pressure from the keel probe, the static pressure from the static probe, and the air density, which, as previously stated, will be calculated. Third parameter will be thrust, which takes velocity and air density, which, as previously stated, are calculated, and we'll take the propeller diameter, which is a keystroke input that the user will put into the front panel of LabVIEW. Finally, the LabVIEW will calculate fuel flow rate for internal combustion engines. This will input the initial mass and final mass of the fuel tank, which are keystroke inputs onto the front panel, and we'll take the elapsed time, which is measured on the front panel. I'll now hand it over to Stephen Woodard.
Thank you, RPV. All right, so ladies and gentlemen, thank you for bearing with us. We know that it's been long and it's been tedious. The moment you've all been waiting for, testing. We've shown you what we've done. We've told you what we would like our test stand to do. Now it's time to show you what it can actually do. Starting off, just in case you forgot, here are what we're supposed to be able to measure. Our thrust from 2 to 50 pounds, we met that. Our propeller RPM, also met that. Our power draw and fuel efficiency, well, that's conditional, I'll tell you why in a bit. And our downstream wake velocity, we didn't meet that due to time constraints. So for our power draw and fuel efficiency, well, there's not a whole lot of internal combustion power plants around for us to test, so fuel efficiency kind of went out the window, and we focused on power draw because electric power plants are a dime a dozen here, and we were successful in that. So, starting off for our designated testing locations, these are based off of the fact that we have limitations. First off, our laptop is Wi-Fi dependent. This is because you need the network in order to log into the laptop, as well as the network for all the licenses for LabVIEW, which makes our portable test stand not so portable, unfortunately. Also, the fact that we need an outlet in close proximity because the test stand, or rather the laptop, needs to be powered because it tends to crash after 30 seconds. This is because writing to an Excel file is very tedious work for a laptop, and the hardware does not meet the design requirements. So in the future, we'd like to upgrade our laptop and some of our hardware. So for our locations, we got the Propulsion Lab. This is because A, it's inside, so our optical sensor works for our propeller RPM. The only downside is that it's on polished concrete, which makes slipping a little bit more likely. However, all of our tests, even on the high end of our electric power plants, we did not reach the slipping thrust. And then for the propulsion courtyard, we recommend that you test either in dawn or dusk, just because the low light conditions help the optical sensor perform correctly. And there's also a surface change, which means slippage is less likely to occur because it goes from polished concrete over to asphalt. Next, we're going to be going over our testing procedures. First off, for the hardware, you got to select your design, test, and configuration. That's up to the user to decide whether or not their power plant is in the push or pull configuration. You don't want to turn your propeller the wrong direction or flip it around. It doesn't work that way. Bad things happen. That's why we have safety shielding. And then after that, you're going to want to install your propeller power plant combination. That's easy enough. You just use the mount bracket here. And then you're going to go ahead and install the shielding. Now that's kind of the pain in the butt part, because when you install your shielding, you have to be quite nimble. We've got connection points down here and there. Make sure you're not wearing any watches, because if you do scratch the paint, I will hunt you down, and that's not very good, because I painted it. As well as the fact that you may cut yourself on the test surface, because it's kind of sharp. And then after you install your shielding, you're going to want to go through the software boot up process. Basically, you want to ensure all of your instrumentation is connected correctly, utilizing quick disconnects as discussed by Nicholas Nagy earlier. And you're going to want to boot up LabVIEW. Hopefully it doesn't crash. Make sure you're connected to the network as well. That's a big thing there. And then you're going to want to zero all of your instrumentation. Make sure that your load cell is actually not touching the backplate when you zero your instrumentation, otherwise you're going to get faulty readings. And then you're going to run your test, and if everything goes well, you're going to rejoice, and then you're going to run another test as soon as possible, otherwise it might crash. So for your testing methodology, we've got our thrust measurement. You want to be under a constant RPM. This also allows you to measure your static thrust and your power draw measurement utilizing our watt meter. Now, we're utilizing the optical sensor, our load cell, and the watt meter. It's actually quite simple and a lot of fun. The only limitations are our laptop. Here's our test. We're going through the boot up process here. And then we have the secondary laptop for the giant red blob, which is our optical sensor. And our actual laptop for all of our instrumentation is outside because we need to be closer to the Wi-Fi. And that's that. Next, we're going to go over our accuracy for all of our tests. So for our requirement, we had to be with an accuracy of 5%, and we're not there. So for our measured thrust, an average for the E-Flight Power 2010 equivalent power plant with the 10-inch propeller, we got a measured thrust of 2.7 pounds with a calculated thrust of 3.7 pounds and a percent difference of 27%. Quite a large difference. And for the E-Flight Power 60, which is the larger range of our power plants that we're going to test for the electric side, we got a measured value of 10.8 pounds with a calculated thrust of 13 pounds and a percent difference of 16.9%. Now the main reason because of these percent differences is because our thrust is average and there's a lot of noise. We talked about that earlier, and the whole problem is that none of us are CEs, SEs, or EEs, and so we don't know how to really get rid of the noise via hardware. That's something that we'd like to do in the future. However, we have tried implementing filters through the software side, but it is recommended that we do the hardware filters first. Next, I'll be handing it back over to David Seneca.
Thank you, Stephen. So I'll be going through the conclusions for the PTS Mark-I. So data acquisition-wise, we collected data from 2 days of testing, and as you heard earlier, we did not quite meet our plus or minus 5% accuracy. And to remedy that in the future, we're going to do further testing as well as implementing filtering through hardware. Requirement-wise, from our RFP, we acquired hardware to measure thrust. We acquired the load cell, we tested it, and it's ready to use. To measure the RPM, we acquired the tachometer, we've tested it, and it's ready to use on a conditional basis, and then it needs low light conditions. For power draw, we acquired the watt meter, we tested it, and it's ready to use. And for fuel flow and downstream wake velocity, we've acquired the instrumentation to measure those, the kitchen scale for fuel flow and for downstream wake velocity, the pressure transducers, and the keel probe and the static probe, but we have not been able to conclusively test those, and they're not ready to use for that reason. Budget-wise, for fabrication, for creating the PTS Mark-I that you see, $224 were spent on the raw materials, and for instrumentation, which was the keel probe, the DAC, and those other components, that was about $700. And the miscellaneous components were such things as the foam padding that went inside, the quick disconnects that were used, and such items were about $40. This came to a total of about $950 with about $46 remaining. It should be noted though that $46 remaining is not including the College of Engineering provided safety shielding, which was $174. And that was provided as I was required to use for anybody to use the test stand, and it was not in our budget. For labor hours, XMod Systems had a slower start in the beginning as we were waiting to acquire our different materials, as well as testing certain things was difficult. Trying to integrate all the different components with LabVIEW created a lot of difficulties. Those were overcome, and during spring break, lots of time was spent. As you can see, there's a sharp increase in the hours where there's a flat line on the blue line, because the blue line is predicted hours and the orange is the actual. And as you can see, we ended up with a 1% difference with us being 10 hours over our predicted amount of hours to spend on the project. Some of the recommendations that we have for the PTS Mark-I would include the downstream wake instrumentation, that a stand needs to be created to support those on the pegboard, as there's currently no stand there. And they also have to be calibrated through a series of tests. For RPM measurement, we recommend implementing some sort of shading in the safety shielding, perhaps making this opaque in some manner. Otherwise, the other option would be to acquire a different optical sensor, which could cost upwards of $600 to compensate for direct sunlight testing. For internal combustion testing, we would recommend that a horizontal mount needs to be built, as that's one of the types of mounts that's used for internal combustion power plants. It was not built this semester. And then fuel flow measurement methods would need to be tested as well. Finally, for data acquisition, a lot of the problems that we had with LabVIEW crashing, as you heard earlier, that was mainly due to the high data acquisition rate that we had and how we were using Excel files to write to. This created a buffering issue with the laptop, and to solve that issue, we could use binary files instead. This would be a lot harder on the user to deal with, and that was why Excel files were used initially. And then we could work with IT to get an improved laptop so that only one laptop would have to be used for testing to run the two different programs. For acknowledgements, we have many acknowledgements that we broke into fabrication, consultation, instrumentation, and software, and testing. We thank all of these people for their help with the project. And at this point, we'd like to open the floor up to questions, and I'll invite XMod Systems up to the stage.
Thanks, great job. What did you do to calibrate the load cell? Did you have any process for doing it?
Okay, essentially with our load cell calibration, we didn't necessarily know that we needed the op-amp circuit to begin with. So we did our initial testing with a series of 5-pound weights that we weighed with the scale to get a little more precise measurement. Once we realized we needed to construct an op-amp circuit, we actually iterated through, I think, 3 different op-amps. The LM324 that we utilize is not an instrumentation op-amp, and therefore wasn't as precise as the other ones, such as the, I want to say, LT1001. That was the desired op-amp to pursue. However, it needed a supply voltage of upwards of 10 to 15, and our DAC can't supply that. So once we were able to construct that op-amp, we essentially had a method of applying those weights in succession that allowed us to create the transfer function of linear progression of that op-amp load cell circuit. And then that's what was used in the LabVIEW to calculate.
So do you think there were errors in that process that accounted for the lack of accuracy?
I would say potentially. That process was iterated about 3 times due to some faulty equipment that was used to measure it. We initially went with a voltmeter, found out that that was reading correct data. Then we utilized a PSU, power supply source, and an oscilloscope to get a more accurate representation. And through those, the transfer functions, we pretty much established that if you have a static load applied, you can be within up to about 1/100th of a pound accuracy, but it's that noise of it jumbling back and forth. And once you actually have the power plant on there and it's creating a little bit of vibrations, that therefore increases the noise. So that's kind of where you would need to focus your efforts on filtration.
If I may add to that real quick, another thing too that would help as well would be incorporating a zeroing function into LabVIEW as well, because currently it's a manual adjustment on the load cell backplate to then verify that your load cell is zeroed. So that would also account for some error as well.
Okay, thanks very much.
Thank you. Good job. When you're looking at how did you calculate the thrust? So you said there was a measured and calculated. So what was the process used to calculate?
Right. So for the calculating of the thrust, it's in the appendix, but basically what I did was I took the propeller characteristics as given to us by the team and their desired operating RPM, and what you do is you take that and I basically used velocity triangles from advanced propulsion class, as well as actuator disk theory, and found out what our velocity was, and then derived our thrust from the downstream wave.
Okay, so how accurate do you think that method is?
So when we were testing the E-Flight Power 60, we had, at one point, we were measuring about 13 pounds of thrust per given RPM, and from my calculations, we had about 13 pounds of thrust. So the only problem was that our percent difference comes from the fact that we're using averaged data, and there's a lot of noise, so trying to find precise measurements within that noise is kind of difficult.
Okay, so what's the error band or whatever associated with that, that noise, if you will? Can you filter that out with Excel or anything? Maybe get...
The filtering would probably be best done through hardware, through the circuitry, to attempt to do that first, and then from that point, if there is any more filtering that needs to be done, to do it in software at that point.
Okay, but you have the data, right?
We have
So
some.
did you try to do software filtering with it? Did you try to?
We did not try to do that, as once again we had a time constraint, and that we needed other instrumentation aspects to work as well. We need to collect data for those as well.
Okay, so your calculated thrust was consistent with some of the measurements, so you had some confidence that was your datum for measuring accuracy.
Right, because we do have the output screen on our LabVIEW front panel, and it tells you what the current thrust is, what it's reading at that moment. And so with the desired RPM that we can see via the optical sensor, and it tells us, hey, you have about 30 pounds of thrust right now at this desired RPM. It correlated to what my calculations were.
Okay, that kind of leads me into my next question is, you've got a lot of things going on, a lot of different types of information coming at you. Can someone walk me through what the user will have to do when they're going to be measuring or when they want to assess the performance of their propeller engine combination? How are they going to get meaningful data? Can you kind of walk me through what they would be doing to do that with the way that the rig is kind of designed now, whether or not you've got all the instrumentation working, but what is the design of what that user is going to be doing to get the data they need?
So at first off, what they do is they set up the testing, right? Put it in their desired configuration. And then once they mount up their power plant, like I said, we do have the front panel where it tells us what your current thrust level is. And the optical sensor that also tells us what
Can you put up, do you have the front panel in a picture?
That is our.
That's it right there.
Oh, so you get the thrust.
Right, you get an
Okay.
output right there, rather than, yes, you can write it to the Excel file, but just as a right now instantaneous, what am I reading?
Okay.
What they do is they will set up the test in whatever configuration that they want. And then once they're operating RPM, they can see what that thrust is. Okay, so they write down what their information is. Now, the point was that we would have to be able to give them an Excel file and say, hey, here's all your data, have fun. But the problem is all the noise. So currently, they're limited to sitting there and writing down what their value is to correlate with RPM. And also
Okay.
limited to average.
So the actual process that they would be going through is once they have all the instrumentation mounted and ready, it's a simple hitting of the measure button. LabVIEW collects the data. Once LabVIEW collects the data, they can go into the Excel file, look at the information they have, perform calculations based on the information they have, whether they feel like they want to take an average of it, take the peak, take the minimum. They can look even at the noise and say, this is roughly where it's at, and take that data, use that for their calculations. That data should be within a fairly reasonable accuracy of what the actual thrust is, even if they're taking an average of it. And again, in the future, what we would want to do is find a way to reduce that noise so that they don't have to do as much digging through noise to find an accurate data point.
Okay, but they could, so does that number fluctuate a lot, that thrust number, or does it hold fairly steadily when you're taking data?
So this thrust on the left is an actual image of data we got from one of our power plants during testing. So it does fluctuate quite a lot, and there are some significant spikes. However, it does stay within a certain range that the user can look at and have a rough estimate of where their thrust is.
Okay,
In
but
this
that's,
case, it would be at about 3 pounds force of thrust if you were to look at this graph.
that's from Excel.
This is generated off of Excel.
Yeah, but that thrust that's coming on the screen,
That dial that you see on the right is not currently on the front panel. That is something that we would want to have that potentially through LabVIEW could be.
but the thrust number that you're getting, is that changing? Can you actually?
Yes, it does. It changes just about instantaneously. So you will see a bit of change on that. You'll see the changes that you see there on that number. So it'll read 3, it'll read 5, it'll read 3, it'll read 4, it'll read 3.
Okay, okay. I think I've got another question, but I'll let Dr. Dan.
On the optical speed sensor, was that mounted or hand operated, or how was that set up?
Duct taped to the crossbeam.
Okay,
It was
so
mounted.
you're looking for the shaft as opposed to a point on the blades?
Correct.
Okay.
However, if a user did want to use that by hand, can be used by hand as well.
Although not recommended.
Not recommended.
Okay. And then go back to the calculations of the downstream wake velocity.
Of course.
Do you intend that to be a single point measurement, or do you intend for that to be traversed?
So for the downstream wake, the way I calculated it was based off of velocity triangles and actuator disk theory. So I have a slide that has my fancy cookies and all. Alright, so everything's based off of the total pressure and what your standard atmospheric density is, and temperature, as well as the propeller diameter. And so with that, you take what your induced velocity is at the hub, right? And initial velocity before the hub for actuator disk theory, because we were saying anything before a test end, it's not moving, it's stationary, so that would be velocity of 0. And afterwards, you take that and you calculate what your reduced velocity is, utilizing the propeller characteristics such as the diameter and the pitch, which then correlates to your alphas and betas and lets you utilize your velocity triangles in the absolute and relative frames in order to find out what your axial velocity is at the hub of the propeller, to be your re-induced, and then determine what your downstream wake velocity is based on the propeller diameter, and then correlate that to your thrust.
How did you determine the velocity of the potato?
My slides that I really didn't put in here. What we did was we took a pressure theory based on pressure vessels, and we said the pressure that is applied to what we assume to be a circular cross-section of the potato going out of the cannon. So we took those pressures and basically using the force off of the pressure, calculating the velocity from that force, taking the length of the barrel, which was 3 feet in our particular case, which the potato had to go through under that pressure, and calculating the velocity at the end of the barrel. From that point, the end of the barrel was placed 15 inches away from the surface of the polycarbonate that was being impacted. So we assumed that that velocity wouldn't drop too dramatically much, and used those for our initial calculations to understand what velocity was impacted.
Did you have video?
Yes, we do not have video in our presentation right now, but I would be happy to send that to you.
That'd be awesome. But can you do a frame by frame? You know what the frame rate is of the camera. You may be able to use that to calculate what the average velocity was from when it left the cannon to when it hit the thing. Just I applaud you for attempting to use an energy method, or like a piston cylinder type of thing. But if you have video imaging, you can go frame by frame. You may be able to get something that's pretty close that can then you can use as a check to see if your calculations were good.
Unfortunately, we were operating with iPads and Android phones, so the frame rate is sketchy at best.
Yeah, you missed the whole thing with the potato, probably. Okay, do you have any? Okay, thank you very much.